Hey everyone, it's time to talk extreme values of a function. So in this video we're going to review the definition of absolute and local extreme values very briefly. We're going to examine the extreme value theorem and local extreme value theorem, and we're going to define critical points of a function and use them to help determine extrema. Let's get started. First up, a brief refresher of absolute extrema. So an absolute maximum or an absolute minimum are essentially the highest points in a function. We often omit the word absolute and just refer to them as maximums or minimums. Okay. Sometimes if an interval is half open or completely open, you may not have a min or a max. But if it's closed and the function's continuous, you're guaranteed a max and a min. This is known as the extreme value theorem. So the extreme value theorem states that if f is continuous on a closed interval, then f has both a maximum and a minimum on the interval. So consider cosine x from negative pi over 2 to pi over 2. It has a minimum of 0 at both negative pi over 2 and pi over 2, so it'd be a tie. It has a maximum of 1 at x equals 0. And then sine x has a minimum of negative 1 at x equals negative pi over 2, and has a maximum of 1 at x equals pi over 2. Okay? Here's some examples of how extreme values could occur at either interior points or on endpoints. Local or relative extreme values are basically high points or low points within some neighborhood. Okay? Note a function has a local maximum or a local minimum at an endpoint C if the appropriate inequality holds for all x in some half-open domain interval containing C. So you may have a half-open interval, and therefore you could have a relative extreme value or a local extreme value in that interval. Super important. Absolute extrema are also local extrema. So if I ask you for all local extrema, you must include absolute in that list if the function has any. Local extreme value theorem states if a function f has a local maximum or a local minimum at an interior point of its domain and f prime exists, then the derivative has to be 0. The extreme value theorem is basically stating if you are a positive derivative, you are an increasing, and then you're decreasing, you have to be 0 at that moment because you can't have a rapid change of increasing to decreasing if f prime exists. If you change from a positive or increasing function, positive derivative, increasing function, to a negative derivative or decreasing function, that is a maximum. Okay, a change of positive to negative. And if you change, I'm going to erase that because I wrote really heavily on it. If you change from a negative derivative or a decreasing function to a positive derivative or increasing function, you have a minimum. You have a minimum there. Okay? Critical point. Super important definition here. A point in the interior of the domain at which f prime is either 0 or it simply does not exist is known as a critical point of f. Critical points are candidates for extreme values. They might be extreme values, they might not be extreme values. You must do a sign chart to test to see if the derivative actually changes sign. Keep in mind a critical point is a coordinate pair x comma y, where the y value represents the function value, and sometimes that represents the extreme value. The x value is the location of that critical point. Here's some key info. Extreme values can occur at critical points and or endpoints. So in order to figure out all the extreme values, you have to consider critical points and you have to consider endpoints. Using a sign chart on a derivative is essential. A function's derivative does not always change sign at critical points. The only way you are actually an extreme value is if it changes from positive to negative or negative to positive. In this, I'm talking about the derivative f prime x. You must change sign in order to be an extreme value. Let's put everything together and try a problem. This one says find the extreme values of this function. Now, even though I didn't give you an interval here, this function actually is unique in a sense that it has its own understood domain. This function is only defined, the domain is only defined on negative 2 to 2. You'll notice that if you plug in values left or right of negative 2 or positive 2, you're going to get things that don't exist. For example, try plugging 100 into the function. You get 1 over 4 minus the 100 squared, which is a really, really big negative number. And you can't have a negative under a radical. Okay? For the same reason, you can't bracket these numbers. Because if you actually bracket those numbers, you would have 0 in the denominator, which is also not defined. So the domain, the understood domain of this function is negative 2 to 2. So keeping that in mind, we ask ourselves a couple of questions. We ask ourselves, first of all, what values would make f prime of x 0, and what values would make f prime of x not exist? These are known as your critical points. Well, in order to populate that list, we need to first find the derivative. The derivative is equal to, let's rewrite this as 4 minus x squared to the negative 1/2. So the derivative is negative 1/2 times 4 minus x squared raised to the negative 3/2 times by the derivative of the inside, which is negative 2x. So if I simplify the derivative, it's simply equal to negative and negative make positive, so 2x over 2 times 4 minus x squared, all raised to the positive 3/2 power, which I can just get rid of my 2's. Bloop. I'm just going to erase them by 2's. And this is my derivative. So the critical points are basically, and we'll actually write them in purple. So my critical points are when the derivative is equal to 0 or the derivative does not exist. So these are my two options. Let's consider the first option first. Well, if I want the derivative to be 0, whenever I want a rational function to be 0, that basically means the numerator has to be 0. What value of x would make the numerator 0? Why, x, of course. So x equals 0 is a critical point. That doesn't necessarily mean it's an extreme value. Okay, does not exist. Well, if I have to make this derivative not exist, you're going to notice that I have the same radical in the derivative as I do in the original. So the negative 2 to 2 restriction is actually going to be good enough. I'm not going to have any values in which f prime of x does not exist. So I'm clean there. Okay? This means I only have one critical point, and that critical point is 0. Let's see what the function is doing at x equals 0. So let's draw a sign chart of the derivative f prime x. Here's 0. Keep in mind I have to live within the interval negative 2 to 2. So let's test negative 1, put it in the derivative. If I put negative 1 right here in the derivative, I get a negative 1 on top over 4 minus a negative 1 squared, which is just 3, raised to the 3/2 power, which is some negative number. Okay? And if I plug a positive 1 into the derivative, I'm just going to get 1 over 4 minus 1. Again, 1 squared is 1, so that's 3 to the 3/2, which is some positive number. So I know I have evidence that this is an extreme value. Specifically, it's either a local or absolute minimum. Minimum. The reason is because I changed from a negative to a positive. So what I look like graphically, I'm going to erase that, is I look like a change in a negative slope, so negative slope, to change in positive slope looks something like that. So I know that I have a minimum. I just kind of usually draw that as a visual to help me. Is it a minimum or a maximum? Okay? Now, is it absolute or is it just local? Well, in order to understand that, let's consider this function. We're only defining this function from negative 2 to 2, right? So at the left endpoint, negative 2, we're decreasing, 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 and then we're increasing, 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 increasing until we get to the right endpoint. That means that this function, even though we've considered all possible values, it will never go lower than x equals 0, which means that x equals 0 is an absolute minimum value. So we'll summarize and say f of x has a minimum of 0, that's the y value, at x equals 0, that's the x value. This is how I'd like to structure our answers. F of x has a minimum of 0 at x equals 0. Example 2. Let's consider the piecewise. Just to save time in the video, let's assume moving forward it's continuous and ask ourselves the question of what are the extreme values. In order to do this problem, we first have to calculate the derivative. So I'll do the derivative right over here. F prime of x is equal to, the derivative of the top piece is just negative 4x when x is less than or equal to 1. And the derivative of the bottom piece is 1 when x is greater than 1. So right off the bat, I can already tell, I bet there's going to be a value in which the function, in which the function's derivative is not continuous. And I think that value is going to be 1. All right, so let's populate a list of critical points. So critical points. Okay, two things I have to check. F prime of x needs to be 0, and f prime of x needs to does not exist. Let's try this first. How can we make the derivative 0? Well, I can make the derivative 0 by plugging in x equals 0, right? Because if I plug in x equals 0, I put a 0 right in there, and I get 0. So I'm going to put a 0 in, x equals 0. That's a critical point. The derivative not existing, x equals 1. Because if I plug a 1 into the top derivative, and I plug a 1 into the bottom derivative, I get -4 for the top, +1 for the bottom. Those are not equal. Therefore, the derivative does not exist at 1. Therefore, 1 is a critical point. So, put them on a number line. 0, 1, this is for the derivative. We're always doing number line tests on the derivative, okay? Now, interestingly enough, we don't have a domain restriction here like we did last time. So I can test numbers like -500 billion. If I plug in -500 billion, I multiply -500 billion by -4, and I get a very large positive. Then I'm going to test numbers between 0 and 1, still defined by the top piece here. If I plug in 1/2, let's say, I get -4 times 1/2, which is a negative result. And then the bottom piece, which I can test numbers to the right of 1, well, they're always going to be 1, so they're always going to be positive. So that's enough evidence to say that at 0, I have some type of maximum, and at 1, I have some type of minimum, because that's the way the slopes are changing. Now I have to ask myself, are they maxes, are they absolutes, or are they local maxes and mins? Well, let's consider the original for a moment. All right, this is the original. I know that the original, as x goes to infinity, f of x, the original function, is also going to infinity. Because if I plug really big numbers right here, I get really big function values as a result. Then, as x goes to negative infinity, I'm now defined by the top piece, and that's also going to go to negative infinity. Because I'm going to be plugging in super big negative numbers. And if I plug super big negative numbers into that top piece, if I do -2 times a super big number, I'm going to get a super big negative number. And the bigger negative I go, the bigger negative the y goes as well. So specifically what this function is looking like is it's towards the left it's going down, and towards the right it's going up. That's enough evidence to say that I don't have any absolute extrema in this example. So that means that both of these guys are locals. Let's summarize. So f of x has a local max of blank at x equals 0. I'll go find that blank in a moment. And f of x has a local min of blank at x equals 1. Well, to find the blank values, I just have to go plug the x's into the original. So let's start with 0. Here's the original. So let's plug a 0 in. So 0 is going to be plugged in this one. I'm just going to get 5 minus 0, which is 5. And then I'm going to go to the minimum. I'm going to plug in a 1. So I'm going to plug in a 1, and I just get the top piece there. So if I plug a 1 in here, I get 5 minus 2 times 1 squared, which is 3. So this is my extreme value summary. All right? One more. Find the absolute max and min for y equals x e to the negative x on 0, 2. So this is a unique example because I actually gave you an extreme value, I gave you thinking ahead, I gave you a closed interval. That means if this function is continuous, which it is, we're guaranteed to have a maximum and a minimum. Okay? So that's what we need to find, a maximum and a minimum. In order to do that, we need to understand one thing, very important, that absolute extrema, I'm actually going to just rewrite that. Okay. Extreme values can occur at critical points or endpoints. Okay? And technically the statement is an and/or endpoints. So we have to check critical points and we have to check endpoints. Well, in order to check critical points, of course, we need a derivative. So let's find the derivative of this thing. Derivative uses the product rule here. So it would be first times derivative of the second, which would be negative e to the negative x, plus second, which is e to the negative x, times derivative first, which is 1. So if I factor out a negative e to the negative, well, let's factor out a positive e to the negative x, I'm left with negative x plus 1. Okay? Now this particular function has a couple of critical points to worry about. So let's populate a critical point list. Critical point. Okay. F prime of x needs to be 0, and f prime of x needs to not exist. So how can we make this thing 0? Well, if we plug in positive 1, then I get a 1 here, and negative plus 1 gives me 0 times the e to the negative x, which is just 0. How can I make the derivative not exist? I don't think I can. I can't plug a value of x in here that would make that derivative not exist. So this does not apply in this situation. However, endpoints apply in this problem. I have two endpoints, x equals 0 and x equals 2, I think. Yes. So that is my list. So we've got absolute extrema located here, potentially, at 1, 0, or 2. How do I figure that out? Oh, I just need to do a little sign chart. Do a little sign chart here, and plug in a 0, a 1, and a 2. Okay, and I know that I'm defined at, specifically, at 0 and 2, I'm going to be closing off my function. So you know what I'm going to do? I'm actually just going to take this. Oh, you know what? I'll teach you a little something else, actually. Why don't we just do this? Let's do the x's. The x means I'm not actually plugging in anything left of 0, and I'm not plugging in anything right of 2. Okay? Now to figure out what these values are, I'm going to get a little help from my trusty calc. So we're just going to scooch this over. Hey, scooch over. Or just not do that. Yeah, we don't want that. Thanks so much. Going to edit that out. Totally going to edit it out. Okay. Here's my trusty calc. My trusty calc is going to help us do these values. So I need the derivative. So the derivative which I factored is e raised to the negative x, and we're going to do parentheses, negative x plus 1. All right, and I need to do a table set of, start at 0 and go up by 1s. So, okay. So in between 0 and 1, all right, I got to get into fraction world. Let's go up by 0.5s. So in between 0 and 1, at 0.5, I'm at a positive value. So positive goes here. Then in between 1 and 2, which is like 1.5, I'm a negative value. And then I know that 2, beyond that, I am ignored. So thank you, trusty calculator. You have served well. You know what? I'll actually keep you open because I'll need the y values in a minute. But let's do some analyzing, okay? Let's do some analyzing. So here, I'm going to move my sign chart over so I can analyze. Okay. What I successfully have just proved is that 1 is some type of maximum. Okay? 1 is some type of maximum because I changed from positive to negative. But let's consider what 0 is. 0 is an endpoint, correct? And what I'm doing past 0 is increasing. So it looks like this. So I know that 0 is some type of minimum. 0 is some type of minimum. Minimum. And additionally, let's consider 2. 2 is an endpoint as well. What's happening before 2? Well, before 2, I'm decreasing. So I'm decreasing until I get to 2 and I stop. That means that 2 is also some type of minimum. Okay? In order to question which one is absolute, I have to ask the trusty calculator for help, figure out the function value, but I know that x equals 1 must be my absolute max because I don't have any others, so it has to be the biggest one. The minimum, though, I do need to ask my calculator which one is bigger, 0 or 2. So I'm going to plug in my original, which is x e to the negative x, x e to the negative x, and I'm going to go to 0 and start at, I'll just go up by 1s because I just need to get 0 and 2. So 0 is 0, so we'll just do y equals 0, and at 2, it's 0.270, And so I'm only considering those values. So that means that the absolute minimum winner is x equals 0. So let's summarize. F of x has an or I won't even use absolute, I'll just say maximum, has a maximum, get rid of the n, has a max of, let's ask the trusty calc, 0.368 at x equals 1, and f of x has a minimum of it was 0. It was 0 at x equals 0. Okay? It's notable to add that I do have a local minimum, which I'll make sure I notate properly in my notes, local minimum of 0.270 at x equals 2, but this question only asked for absolute extrema, so I do not need to include it in my list.